Okay, this lesson is a lesson on how to calculate the change in enthalpy for a target reaction using different thermochemical equations given to you. What Hess's Law tells us is that we can approach determining enthalpy for a reaction two different ways. We can use different thermochemical equations and manipulate them so that we can cancel things out and get to our target equation, or we can use the sum of the heats of formation. This question looks at determining the enthalpy of a target reaction using other thermochemical equations. So we've got an equation here where we've got iron 2 oxide and carbon monoxide giving us iron, elemental iron, and carbon dioxide. Obviously we can't do this in the lab, but we do have some data from other reactions that might allow us to determine what the enthalpy for this reaction is. So we've got three different reactions here on the left. Now whenever I do these questions, I like to put my starting, my thermochemical equations that were given to me on the left, and I number them off, and then I draw a little line here because on the right hand side I'm going to do my manipulation. And then you'll notice I've got these straight lines here, and it's once you manipulate your equations and you've got your what you've done to your enthalpies beside that, you can then just do a straight cancel and sum what you've got. So I look at my target and I say, okay, I need to get my iron 2 oxide on one side plus carbon monoxide on the left and elemental iron and carbon dioxide on the right. So I look at my equations and I say, what do I need to do to each one in order to get to my target? So I look at this first one and I can see I've got iron 3 oxide, and I've got carbon monoxide, and I've got elemental iron, and I've got carbon dioxide. So let's see what I started to do. So I left this equation the same, except for I realized that I had to divide everything by 2, because in my target equation I just have iron by itself and I have a 2 in front there. So I divide everything by 2, all my coefficients by 2. I also have to divide my enthalpy by 2. So then I look at the next equation. I say, well, what do I need to do here? For this equation I divided everything by 6. And that is going to, the reason for that I'll show you after we look at this next part. Sometimes when you do these questions, you have to look at where you want to go, look at all the reactions and say, okay, I have to manipulate these two first, and then there will be another one that's sort of in the middle that I use to balance everything out with. Number 2 is my balancing equation. So actually when I did this question, I looked at 1 and 3, did my work with them first, and then I went and changed everything up. So if I look at equation number 3, I've got 3 iron 2 oxide on the right hand side. I need to get that back on the left. Now I've got a 3 in front there, so what I did was I divide everything by 3. And so once I divide everything by 3, I'd gotten this was 1/3 CO2 and 1/3 CO, 1/3 Fe3O4. Then I took a look at number 2 and I saw, okay, now what am I going to have to cancel out? Well, I have 1/3 Fe3O4 here, and in this equation all the way over here I've got a 3 out front. So that meant I had to divide everything by 6 in order to get that to be 1/3. So I had to do number 2, was actually my last equation to manipulate, and I had to divide all these coefficients by 6. And so that's what makes this question a little difficult, was because I had to divide all these by 6, and then I had to go back and change what I'd done in question 3 and make them out of 6s as well, and out of 6. as well, just so that things would balance out. So what I did was I balanced out the easy things first. So these lines show what things can balance out right away. But I'm going to have a bunch of carbon dioxides and carbon monoxides, and there's going to be fractions, and it's going to be pretty nasty. So I figured I better put a middle step in. So this is my middle step right here. So what I did was I looked at my fractions of carbon dioxide and carbon monoxide. So initially it was 3/2 CO, 1/2 CO2 on the left side, and it was 1/2 CO and 3/2 CO2. Now if I have 1/2 CO2 here and I take 1 from 3/2, I get 2/2 CO2, which is 1. And oh, lo and behold, I only want 1 CO2 there. Same thing here. I had 1/2 carbon monoxide left over, and I had 3/2 of carbon monoxide on this side. So if I take 1/2 from 3/2, I'm left with 2/2. 2/2 is 1. And holy man, take a look at that. I now get a chance to balance everything out, and I get my target equation. Now, when we go back, we see that in this first equation, I had to divide everything by, I divided this by 2, so which is what I did with my enthalpy. Here, I flip things around and divide by 6, and in this one, I flip things around and divide it by 3. And so once I've done all that, I get, and I add these up now, I get my enthalpy, minus 17.4 kilojoules per mole. And that is how you would do, this was a pretty tricky one, but that's how you would use Hess's law to manipulate thermochemical equations to determine the enthalpy for a target reaction.